Hiya. Right, well done sticking it out. So the next, well, I'm hoping 3, let's see if we can get through it in target time, lectures are about another Apache project which sits on top of Hadoop and HDFS, although it can run without them. And this is Apache's Spark project. So I guess about 2 or 3 years ago, Spark was the kind of new kid on the block, and it was all, oh, Hadoop's dead and Spark is the new thing. And that's all kind of settled down now, and people realise that, you know, they're different things and for different purposes. But Spark is still, you still see the word Spark in an awful lot of job adverts at the moment, and it's still kind of, you know, an area where employers are pretty keen on finding people with some skills. So, I should tell you about it. So, as I said again, it's another Apache project. It's open source, and it's based. It kind of came out of the Hadoop project. It's based around MapReduce again. You can run it on Hadoop, but actually it also has its own cluster management system. So you can install Spark and its cluster management itself without having it running on top of Hadoop if you want. And its main selling point, and why people got excited a few years ago about it, is that it runs in memory rather than relying, as Hadoop does, on passing things around, well, storing things on disk and passing them around from disk. So the people who developed it ran some tests. I suspect they were fairly carefully chosen tests, but they've shown that on certain things, certain benchmarks, it will run up to 100 times faster than Hadoop. And this is because it's running in memory, right? So if you pick the task and it can all run in memory, then it'll run an awful lot faster. So those of you who are fed up of waiting for Hadoop to do its business here might think that that's quite exciting, but that really only kicks in on large volumes of data. What we're experiencing is the overhead of starting the thing up and shutting it down again. The time it takes to actually run the code on the small data sets that we're using is nothing. So actually, cutting that by 100 really wouldn't make any difference to us. But on the type of data set that this is all designed to actually use, large ones over large clusters, obviously something that took 100 days, being able to run it in a day instead, makes a difference between not being able to run it at all and getting an answer in sensible human time. And it also has an advanced set of it has an advanced set of libraries around it for doing all kinds of much more interesting stuff, as we'll see in a minute. So that's the basic idea. It supports 3 different languages. You can do it in Python, which is what I'm going to be doing. You can do it in Java, or you can do it in Scala. It was written in Scala, so in some senses this is its kind of native language. You might choose to interact with it in that, but I don't want to inflict another programming language on you at this stage, so we'll stick to Python. To be honest, the examples I'm giving are just little illustrative ones, so this course isn't about learning any of these in great depth. It's really just to show you what kind of things can be done. It has a set of advanced, some libraries, some algorithms that are included, all written to run on top of a distributed cluster. And there's some pretty clever stuff in here. So and things like SQL, like queries, a bit like Hive that we talked about earlier, right? Once you've got your data in, you can use Spark SQL. I think they were hoping people would pronounce it Sparkle, and run SQL like queries on your data. It has this nice interactive console where you can, because it's so fast and because it's not starting up and shutting down in the same way, you can actually type command after command and get answers back and keep things in memory. So you can do a map, get the results of that map in a variable. I'll talk about how these variables are structured in a little while. Then do something else to that, and then do something else to it interactively. So it's a lot nicer to interact with. It has modules for coping with streaming data that's just constantly coming in and being processed as it arrives. It has a whole bunch of machine learning algorithms implemented. So this is nice. You can actually get your data distributed across the cluster and run regression on it, for example, using the regression, for example, it uses gradient descent to take examples from all over the cluster and minimise the error and so on. And also it has ways of representing data as a graph and methods for traversing the graph and so on. So quite a lot of ready-made, sophisticated stuff for you. I mean, you wouldn't want to try and implement even a regression algorithm in Hadoop the way we've been doing it, right? That would be a little bit of a challenge. So you can deploy it either on top of HDFS, that's what we've got here in the department, you can play around with it if you want, where Spark and MapReduce run side by side on HDFS. You can use, so I haven't really talked about Yarn at all, but it's the resource manager for Hadoop. I'm trying to stick to the programming side rather than the system admin side, so we won't really meet Yarn. But you can use Yarn to integrate Spark into Hadoop. Or you can have it running on its own and making use of the MapReduce process. So there's a few different deployment options. I won't go into them because, as I said, I want to talk a bit more about programming it and a bit less about system administrating it. So I've already talked about a few of these things. We've got Spark SQL. And really, if you think about how I described Hive earlier today, this idea that it abstracts the data, imposes a schema on it, and allows you to type SQL-like queries. Basically the same idea, but you're doing it from, well, let's say from Python, if we're doing it in that way. Talked about the streaming one, the machine learning library. There's an ever-growing set of machine learning algorithms that you can use, and framework for computing graphs as well. So I think some of you met graphs in the last semester. Okay, so it's kind of vague idea of some of the things that it's got, but this is the kind of fundamental thing to start to understand if you actually want to start using Spark. And this is the idea that you define a variable that is associated with the data that you're manipulating. And normally when we think about a variable, we think about something that's stored in memory on our own computer. Maybe it's a data structure. I'm using variable in the loosest sense, an object. And we run the program, and we can manipulate the variable, and it's there in memory, and it goes when we're finished. So think about that idea for certain data structures, but it's not stored in memory on our computer. It's stored in memory distributed across the cluster. Right, so this is Spark's party trick. This is the kind of key to why Spark is interesting. You set up one of these, they're called Resilient Distributed Data Sets, RDD. And so this might be an array or a vector or a matrix or some sort. And once you've defined one, then it's immutable. So you set it up, and there it is in memory, fixed. And depending on the programming language that you're using, these things can be objects. For instance, a Java object or a Python list, or whatever it is if you're using these different languages. And behind the scenes, invisible to you, it divides it up into some kind of logical partition, distributes across different nodes, and it's stored and operated on different nodes. So let's say we have a matrix, I don't know, 1 million columns by 5 million rows or something, a great massive matrix, right? And we want to do some linear algebra on it for machine learning purposes or some such. Well, we can't store that on the one machine. So Spark, for us, well, where does it come from, first of all? Well, let's say it starts off as a file, right? A great big file with many rows and many columns. So it reads it from a file into this distributed memory, resilient distributed data sets. That's what the idea of this thing is. Reads it in. And then from, let's say, keep it the simplest version, you type from the command line to tell it to do something to this matrix, and behind the scenes, it works out how to do that. So if we want to, I don't know, scale the matrix by a value or some such, then we tell it to do it, and it works out how all of the nodes with different bits of the matrix have to communicate with each other to carry out that operation. And when it's done, you have a new variable, which is the result, a new RDD, which is the result of doing this, which you can then either collect to see what the contents are or do some further calculations on or whatever. So that's the basic idea of it, but the cleverness is this business, that it keeps it in memory, and that keeps the operations fast. So, well, I think the reason why you might do this is pretty obvious. So in MapReduce on Hadoop, there's an awful lot of disk I/O, writing from one machine to another. And as soon as you start to use the disk, that's what takes time, right? If you can keep things in memory, it's all nice and fast. So as long as we keep everything in memory, even if there's quite an overhead of communication to try and maintain one data structure spread across machines, as long as we're not writing to disk, then things can happen an awful lot quicker. So that's the main idea. And there's also this idea that it stays in memory even when the step that you've just asked it to perform has completed. So MapReduce, you kind of experience this now, is a very linear thing, right? It does the map, sends it to the reduce, gives you the results. You might open the results and want to do another, maybe use those as the input to another MapReduce or some such, and then you've got to start the process again. Whereas here, these things, if you tell them to persist in memory, it keeps them in memory so that you can perform any number of operations on them without having to start up the process again. So you've got much quicker access to them. And that allows us to chain together job after job after job if we want, without having to start the whole process again, and without having to read from disk in between. So the whole thing, as long as we can keep it in memory, is an awful lot quicker. And because it's kept in memory, because it doesn't get deleted from memory each time we run something, that allows us to have an interactive console. That allows us to type in a command line, let's say, open this file, read it into a RDD, and then do something to that and get the result, then do something to the result, and so on. And these things aren't lost. So you probably, those of you who did the Python course at least, are used to the idea of an interactive console. You can declare a variable, a equals 1, and then on the next line you can type, I don't know, a equals a plus 1, and then on the next line print a, and you get 2. And there's this idea that these things are kept in memory for you as you interact. So it's the same idea, except now it's not just kept in local memory, it's kept in the distributed memory of the cluster. So you now have this large number of machines at your fingertips, if you like. So, for example, you use PySpark if you want to use it in Python, and once that's running, you get an interactive Python console, and so you can type local Python commands, create local variables, just as you always have done, but you can use the Spark API commands as well to make use of the cluster. And this whole interaction with the cluster is done via a single variable that's called SC, that's the Spark context. And that's instantiated for you when you bring up the console, and it's a reference to the environment in which Spark is operating. So we have a very simple example of it here. I'm declaring a variable R, and I'm saying from this Spark context, open the text file with this name. And that one line takes the contents of that text file, which is somewhere in the file system, reads it into a variable that's called R, or at least makes it available to a variable called R. When they're executed, it's a little more clever than that. It doesn't do stuff until it really needs to. So at this point, it knows that at some point in the future, I'm going to try and do something to R, and when I do, it's going to need to get that file and put it into it. But it waits for me to do that before it actually bothers to do so. But basically, we now have this RDD called R, which is the contents of that file in memory, ready for me to do something to it. And it's not in local memory, remember, it's spread across. So then we can use the Spark API to perform operations on that RDD, and the way it's organised, so that we've got these things called transformations, which just change the data, and actions to perform on these RDDs. And those of you who have done Python before, which I suspect is a chunk of you, if you haven't, it's not a big disadvantage, you'll see the idea as we go along. It relies quite heavily on the functional programming aspect of Python, so lambda functions, for example, for those of you who use them, feature quite heavily. I'll show you some examples of doing that later on. So for example, if we say map, which is the Python map function there, and we send in a function to that, then it goes through the RDD that we're calling it on, that data structure, and it runs that function on every single entry in that variable. So if we declare what that function is and then send it in, that's how we say, do this to every entry in the data structure.
Entry means lines?
Sorry?
Every entry you mean lines?
Yes. I mean, in a simple text file it would be lines. Because these objects can be richer than that, but yeah, for now let's say lines, because I've read something from a text file. That's what my examples were. Now, so here is the really simplest way you might do that. I'm kind of cheating here because I've got one word on each row of a file, right? So actually, the file is just a great long list that they've been in Python. So I've got a file.text, which is basically a long list of words. All right. So I say R is text file and the name of it. That makes it available to my distributed variable. Then R.map, so that's saying run the function that's in here on each row of R. And I'm using this lambda function, probably most of you remember how you do this. So I'm saying that take each entry, in which case at the moment it's just a word, right? I've been careful to keep it a word on a row at a time. So it just takes the word one entry at a time, and it outputs the word and a count of 1. All right? So all that stuff that we defined in our mapper for Java has been boiled down to this. That's the same as that first word count that we did, right? We're taking each entry, except for the splitting, and we're sending it out with a count of 1. So that's what the lambda function defines. So we're just putting the word and the count of 1. So that's that bit, given the inputs there of word. So I've taken my original file, put it into a variable, run that process on every single entry in it. Remember that at the moment these entries are just single words, just to keep things simple for a moment. And that's counted. But there's a bit of a simplification, right? You don't tend to have just one word per line. So actually we want to do that split, a bit like we did the split in Java. So let's do that. Now we've got many words per line. So what I'm going to do, first of all, is create, so this text is this is the RDD that I've read from the file. So I'm going to create a new RDD called words, which is the result of doing this flat map, which just reads each line and produces a new line in its output for each time this is run. So basically it's splitting it, and then each thing it finds in the split, it's sending out to be a new line. So it's kind of converting it into that one word per line format that I had it in originally. So then we can take the output of that, my words. If I'm typing this interactively, it remembers what these are, so I can do it a line at a time. Same lambda function as I had before. And now to get the word count, so this is the end version of either of the methods I just showed you, I can do reduce by key, so this automatically will treat the first half of this as the key and the second half as the value. I'm defining a lambda function. Now this one's slightly different. I'm getting two values, A and B, as the input, and the output is the result of adding them together. Okay, so that's slightly, well, considerably different from what we're used to in our Java reducer, because now the A is an accumulator. In other words, it's the results of the previous call of this, and B is the new value. So if we're working our way through a list of numbers 1, 2, 3, 4, 5, the first one, A, will be 0 because we haven't done anything. B will be 1, so A plus B will be 1. The next time round, A will be 1, the result of just doing that. B will be 2, the second one in the list, so 1 plus 2 is 3. Next time round, that will be 3, and so on. So it's adding an accumulator. So that's different from what we used to in the Java reducer. Okay. So basically, that is the entire word count example that I gave you in that first Java example. So you can see it simplified things quite considerably. And here it is. I suspect you can't read that, sorry. But here it is being run anyway on that via.txt that we've all grown to love from the labs. And you can, well, maybe you can't see. Can you see at the back? Okay, I'll quickly talk about it. Suspecting we have to spend 2 sessions on this set of slides anyway. So, sc.txt file via.txt, that's me reading the text file into an RDD that I call text. And then anytime if you type the name of the RDD.collect, that grabs it from memory and displays it on screen. So you need to be a little bit careful when you do that, because it's massive. You get an awful lot scrolling up, but here it is, it's quite small. So I've grabbed it, and all it is the string. All these U's just indicate that it's a Unicode, you can ignore those. So yes, here's the file, that's what I was expecting. Then I do my flat map and collect that, and you can see how it's split it into individual words. Then I do my map, I collect that, and I've got each word with the count of 1 after it, so I can actually see how it's going step by step. Then I do my reduce by key here, and finally collect it, and I get the counts. I is 3, is 1, when is 2, and so on. So in those few lines, not only have I reproduced all of that MapReduce stuff that we did in Java, but actually it's a lot more pleasing, right? Because as I go along, I can see where I am, rather than having to run the whole thing and then work out where on earth the error was. So you can see at any stage if you don't get what you were expecting, at least on a small one like this, obviously not on a huge file, particularly the first step. But at least, you know, it makes all of that a lot easier. And if we want to be clever, we can chain it all together into one long statement. So I've already got the file, and I'm doing my flat map on it, splitting it on the results of that. So you chain stuff together by just putting a dot after the previous one. So the results of that dot map dot reduce. So it's all in one. So now I've reduced the, I'll use the word, now I've reduced all of that Java that we had before into a single statement. So, but really I think if we hadn't done all of that stuff and I'd just gone straight to this, you really wouldn't have a lot of insight into what on earth that meant. Is that quite, yeah?
Yeah, just want to ask, is this in Python?
This is in Python, yes. Yeah. So I talked through this when it was up, but this is a summary of what I said about that. The reduce by key function is different from the way we're used to getting it, where we're used to getting the key and an iterable list of all of the values associated. Now the key, well here, the key is hidden from us, and all we get is an accumulator and a value. And the accumulator becomes the result of whatever we did in the function when we called it. So that's the way the reducer works there. A bit like, oh well no, actually we didn't really look at that. No, doesn't matter, sorry. Okay, so that was on a flat text file. We can also process tabular data. Now I realise, actually the slide, if you're following online, I realise I've put this 1 year, I did an assignment that used this car owners data, but it's not the assignment you've got. So I expected you to know a little bit more about this file than you do, but I can describe it pretty quickly. It's a tabular file, columns about people who bought cars. So some of the columns are demographic information about the people, and some of the columns are information about the cars that they bought. One row is a single person and the car that they bought. So all you need to know from this slide is that that file is called carowners.csv. Sorry, missing quotes there. And column 5 has the model of the car in it. Okay, that's really all we need to know. And so the bit of interest here really is that once we've got it into memory, we're doing our map again. We're doing a lambda on a single entry, so that's one row from the file. We're splitting it on a comma, and then this square bracket 5 says take the entry at index 5, so the 6th column, if you like. And output that with a 1, and then do the reduce actually in the same way. So here we're doing a count of the different values down that particular column. And the only new thing here is the fact that if we're reading the CSV, we can do a split and then treat it as access it as an index of an array right there. Or we might want to filter it. So here, pretty much the same example. I'm doing a map where I take each row, split it, take out the car model, and then this is the new bit, dot filter. So here, we're taking the A and the B, that's the value from here, and the key from here and the value associated with it. If the key is MX5, in this case the value from that column, then we keep it. If it isn't, then it just gets ignored. So now actually we're just going through looking for the MX5s, and then we pass them on to the same. So basically this A and B here, it centers A and B here, but we're just checking, sorry, we're not quite the same, that's a bit confusing, maybe we should have used different letters. That one is from that column there, and then that's the same as the accumulator that it was before. Yeah.
Is this point of view for MX5 mandatory or optional?
I think it's mandatory actually. I think it doesn't work if you don't put it there. This saying that it's a Unicode here, I think it's mandatory. Yeah. I can't imagine I would have included it if it wasn't. Yes, I'm pretty sure it is. Easy way to find out. Yes.
Even in numbers, is that has to use a view as well?
I know that refers just to strings. Just to strings.
This is.
Yeah. Yeah. In fact, here's a perfect example. So column 0 contains an age. So here we're doing pretty much the same thing, where we're looking at column 0 and passing it if it's greater than 50 and everything else is.
You can put filter before or after the map is the same?
Well, yeah, so it's just, they're all, they can all go where you want them. It depends how much work, you don't want to do a bunch of work and then filter it, because if you needn't have done that work before you filtered it. So yeah, it's, think of it as a pipeline really.
And the previous one, the filter would be...
I think I probably could have done, let's have a look. Oh well no, we needed to do the split. The filter is pretty much the first thing. Actually, so did I bother to do the split? Is that what the... Oh well no, I'm just... Yeah, I'm splitting every time, this time, but perhaps for reasons that occurred to me at the time, or perhaps just to show that you can do it like that. Yeah, it probably would have been more sensible to split it once and pass it through, but yeah, that's, maybe it's just to show different ways of doing it. Okay, so there's a few kind of simple examples, difficult to take in a lecture, I realise, but fairly straightforward to start to play around with if you're sitting at the keyboard. The one thing you will realise as soon as you start to do it sitting at the keyboard is that the console in its default state is very verbose. You get a whole bunch of warnings and all kinds of stuff that you don't really need to know about. So it has a number of levels that you can set. Warn is probably the best one. That tells you if something's wrong but misses out a whole bunch of other stuff. And here are the other options, all being the one that spews all kinds of things. Or you can just turn this off completely. But it's definitely worth at least setting it to warn, otherwise finding your results in amongst the rest of it is a bit tedious. How are we doing? Not bad. Right, okay, so I've talked about these RDDs, these distributed memory objects, and I've given you the first example of how to create one simply by reading it from a file. And that seems like the most commonly used logical way to do it, right? The point is that these things are very big. You're not going to be typing one in at the command line, but you can, or perhaps you might generate a massive one by performing calculations on data or running experiments that generate data. So let's just have a quick look at ways of getting data into the systems that isn't just reading from a file. So here, for example, now remember we're back in Python. So here, this is just a Python variable, and I'm defining this Python object here. And then all I do to send it into Spark and turn it into an RDD is use the sc.parallelize function and send it into that. Right. So here it is, Python object, send it into here, and out comes this RDD. Now obviously there's not a lot of scope for distributing that, right? It's probably just there on the machine. But once you've done that, you can at least now use the API and play around and so on. So it doesn't really matter if it's small and can't be distributed. Sometimes it's just useful to use the framework and some of the things that are around PySpark, just because they're fast and easy ways to manipulate your data. So if I now say r.collect, it grabs it from here and feeds it me back in the same format. And you might do it with other things. So here I'm doing it with a dictionary. So here's my Python dictionary. Then I just sent straight in, and so I get out here this RDD that's the result of parallelizing that dictionary. Yeah.
So the last one, you go back. The last one is what I see. It's like there's no brackets at the end. Is that?
Have I missed some?
Telling us
Oh, sorry. Yeah, should be a round bracket there, shouldn't it? Yeah. I need some way of editing as I go along and save me. Some of them get done, and I must admit some of them don't. Right. So, although we can send in any kind of data structure we want, we're now kind of aware that key value pairs are, the model that is behind a lot of the way a lot of these things work. So we can produce these key value pairs in the data from the start, or they might come out of the results of doing a map. So that's what naturally comes out of the map, right? The key value pairs. They might come out of a file, or even something like a JSON object with the name as the key and the value as the value, right, from the JSON object. And so here, I'm doing some very simple stuff, just line by line. Here I've got my key value pairs, just as a list of tuples. So A1, A0, 3, B10, B5. And then if I do r.collect, I see that they come back in the state I expected. And then because they're already key value pairs, I can immediately just say R reduced by key. I'm going to treat this as the key and this is the value. And when it's run that, I get back two keys, A and B, right, because there's two different values in there, and the sum from each, 6 and 15. So that one line now has done the reduced stage, and again, I've just added them. Follow that? Okay. So, so far we've used the lambda function, which is nice and quick if what you want to do is small, but not so good if you want to do something a little bit longer. Although my example here isn't particularly long, but you know, all the same. So all I've done here is define a function ahead of time. I called it max. It takes two parameters. It compares one to the other, and well, you might guess it returns the largest. So I can define that. Again, this is just local. Define it in Python. I can test it. What's the max of 1 and 2? It returns 2. Okay, that seems to be working. So here I'm just getting my collection back to show you that I've still got it. There it is. So now if I do reduce by key max, then what it's going to do is group together all the A's, group together all the B's. On that set, run the function, and it finds the maximum of each. Okay. So the only difference there is I'm passing in max here to mean this function here. So that's what I want run when I do the reducer. And it's run that function across all of those keys. And it knows that this is the key and this is a value. And that's the assumption that we're all working under. Okay? Right, okay, so how are we doing? Not bad. Right, so there's some examples of just a few lines of code doing the kind of thing that you might want to do in a MapReduce. But as I mentioned not very long ago, we've got a much more flexible approach. So when I talked about it with the chaining of things one after the other, I said you do a map and a reduce and then another map on the results of that, and then something else is split and so on. But actually, you can be a little bit more powerful than that. You can define what is known as a DAG, a directed acyclical graph. And the purpose of one of these is to define a series of operations that happen starting with some original data source, and then, for example, it might split in a map so that we get a split one for each key, and then for the different keys there might be an operation on it, and then perhaps they all converge to a final reduce or some such. So it's directed because we say what the direction of the flow of the data is. Okay, we say it starts here, it flows from one process to another, so that's the direction. It's acyclical. That means that if it's come out of this process and got to that process, it must never be able to get back to that same process again. Okay, it's going along in a line. There might be a map followed by another map, but it can't be. Otherwise, it would go around forever. Okay, so we don't want cycles. And the graph bit, that's just nodes. The nodes are processes, and the lines are, the data flow from this one to that one. So quite often your graph will actually be a pipeline. The data starts here, it comes in, it comes out to this one, it comes in, it comes out. But you can have it so that it splits maybe on a key, maybe on some kind of a condition. So actually it's a bit more like a tree as it flows along. So because these processes are all distributed, then we end up with these branches in the graph. So that's kind of a little bit more advanced, but I thought I might at least tell you of its existence. Now I've already mentioned this. As we're interacting on the command line, the variables that we're declaring are not immediately lost. But there are some circumstances where you do need to clear memory and start again. And so there might be some variables that you want to persist. So if there's a particular RDD that you want to keep in memory for longer, then you can say the name of it .cache, and that tells Spark that you want to keep hold of this when everything else is finished, because you're going to make use of it again later. So that's how you preserve your RDD for longer.
How does it know when we are finished?
I knew you were going to ask that, and I can't remember. I think you tell it, actually, that it can clear its memory. I'll check for you. So as soon as I started saying this, I know what the question's going to be. In fact, I haven't. I remember being in a similar position last year and knowing the answer, and now I can't remember what it is. So that's not very good, is it? There is one. Oh, it'll come back to me probably 5 minutes after we leave the lecture, and I'll send you an email. Right, yes, okay. So far I've been showing you an interaction in a console. That's not really the most... It's nice for learning and it's nice for playing around. But actually, because it's Python, now you can write it into apps. You can write yourself a proper Python program, run that, and it'll run all of the steps interacting with Spark as and where you need to do it. Actually, that might be one of the answers. Once the program's finished, you cache it for the next program. That rings a bell, but I'll check. Certainly that's it. So if you want to do that, there's only a couple of things extra that you need to know. The first is that you're going to need to import the right library. So from PySpark, import Spark context, so that they're able to get hold of that context. And then we set this variable sc is Spark context, and I can't remember what I know those two parameters mean, so I'll come back to that as well. Maybe it's too late in the day. So, actually I think those are just names that my app at least is just a name that you've given it. Okay, so we do those two things. We open the text file, we collect the data into a local variable, and when we print it, it prints out the results of what were in there. And then we can run that all in one go and see it run. So in the Hive lecture, I said to you, I realised that I wasn't sure if you could access Hive or not. I don't know if anybody's tried it in the hour in between, but you can. The stuff I told you about where Hive was in the previous lecture, that's true. This is how you access Spark. We connect to Hadoop in exactly the same way. We run PySpark, set the verbosity level accordingly, and then we can do whatever we want to do. If we want to read from our local file, because remember now we're on the local machine now, so if we want a local file, then that's where we are. So we can just use paths straight from our H drive. But if we want to read from HDFS, then we need this extra local host and port number to tell it where to look, because it's on the local machine. So basically, that's it. 2 slides to go, that's all right. So if you want to write a script and run it to try it, then none of this making jar files and so on. Just write the script, put it in a folder on your H drive. So I suggest that's just where you create it, right? You don't need to copy it from anywhere. Create yourself a folder on H called Spark, put spark.py in it or something. Put that, whatever your code you want to run it into it. And then wherever you put it, once you're in Hadoop 0 in the normal way, change to there. Use a loop Spark being PySpark, and then the only extra bit is the name of your program.py, and then that runs it. So if you ran that code that I gave on the previous slide, then that would do that. And then the output of your program is kind of mixed in amongst what Python is churning out as well, so that's why you want to turn down the verbosity a bit. Okay, so that's just about it. There's 2 more lectures on Spark, by the way, before you think, I'm not sure I learned much about that. So we've been doing it all in Python. For those of you who are interested, you can do it in Scala and Java as well. And there's some stuff that you can do from R. You can use the data frames in R to use the Spark SQL. Right, so that's the first.
The command prompt. If you write Spark, you will see the command prompt in the lab.
Yeah.
Do we have lab for Spark as well?
Good question. Yes, there is one. Yes.
Can we write Python in the command prompt as well?
Yeah. Yes, it's a Python command line. Yeah.
It's actually the memory which we can use for Spark.
Yes.
The sum of all the runs of all the cluster nodes. Or how large is the overhead?
Well, essentially, yes. But then it depends. You know, it depends who's using it and how it's allocated. And of course, they're doing other stuff.
Yes.
But yes, basically, there is an allocation across all of them.
Basically, it's a limitation. Basically, my cluster has only, I don't know, 120 megabytes.
Oh, yes.
Gigabytes
Yes.
of RAM.
Yes.
So basically, all the variables we could hold is about 100 gigabytes.
Yeah, yes. If you build your cluster with one file,
Yes.
then yes, you're going to run out of memory. Yeah. But I don't know. You pick the use cases.
Yeah, keys.
Yeah, but that's what you run the fact the program with PySpark.
Yeah.
It's not library in Python yet, is it? It's not PySpark program.
Oh, I see what you mean. No, yeah, running. Yes, running with PySpark. Yes, it needs to know that it's running with Spark. Yeah. Yes, it's not quite so simple because it's not running on the local machine. You need the whole cluster management thing running. Yes, so it's not. Yeah, which is why it needs to run Spark.
System runs over.
Yeah.